Welcome back. This video is section 6 in chapter 19, and today we're talking about activators. Now, activators create a situation where the aromatic ring is more reactive than just benzene. So if we look at benzene, which has just a hydrogen here at the top position, there's 6 hydrogens, but I have to have a point of reference to compare. This has a certain reactivity because these pi bonding electrons act as the nucleophile to attack an electrophile, and that's usually the rate limiting step to go on to form eventually the product after all of the reaction is all said and done. Okay, and as we know, the electrophile, bromine, chlorine, a nitro group, so on, will replace that hydrogen in an electrophilic aromatic substitution reaction. Now, if you have an electron donating group, okay, so electron donating group, I abbreviate EDG just for short, but I'll just write it out here in case you're taking notes. So this is an electron donating group, okay? Now remember that the pi bonding electrons are a source of electrons, and this curved arrow we draw is, the electrons moving. So in order to draw this kind of situation, you can think of the electron donating group as donating electrons into the aromatic ring and making the pi bonding electrons more electron rich. So I'm going to embolden these pi bonds that make up the benzene ring, okay, to try to emphasize this. And when the pi bonding electrons attack an electrophile, they're much more readily able to, and so I'm kind of using a bold arrow to denote that, and that's going to attack the electrophile, and that's going to be faster. Okay, so that's what the word activation implies. So electron donating groups are activators of the aromatic system. Okay, now you have two types of activating groups. The first type to very easily understand are the pi donors, okay? Now these substituents have this general form, Z, all right? And there are lone pairs on this atom, okay? So Z can be oxygen, nitrogen, sulfur, maybe a halogen. We'll talk about halogens at the end, but these are electron donating groups, and they're pi donating because these lone pairs are conjugated. There's a resonance structure you can draw, and these are in a p orbital, okay? So we draw curved arrows to show how these electrons can move down into the ring, and let's draw the first resonance structure here. Okay, so look where the negative charge is. The negative charge is on a carbon that resides on the benzene ring or the phenyl ring. Okay, another resonance structure we can draw is this one here. And again, if you look at the negative charge is on the phenyl ring, okay? It's on the carbon here at the para position. And let's draw a third resonance structure here. So you have three principal resonance structures with a charge at the two ortho carbons and the para carbon. So if we were to draw the resonance hybrid, which we normally don't draw in organic chemistry, we would draw the sigma bonds all like this, and then the pi bonds are smeared out everywhere. There's a partial pi bond to the Z substituent, and there's partial pi bonding between all the carbons of this ring. And if we write where the positive charge is, we would write delta plus on the Z substituent, okay? It's positive in 3 of these 4 resonance structures, so we write delta plus on the Z. And then there's a partial negative on this orthocarbon, a partial negative on this orthocarbon, and a partial negative on this paracarbon. So the molecule as a whole is neutral, but because of the effect of that electron donating group, it enriches the negative charge character at the 2 orthocarbons and the paracarbon. As a result, electron donating groups are ortho-para-directors. The nucleophilic atoms, in a sense, are going to be the 2 orthocarbons and the paracarbon. Okay? Types of pi bonding electron donating groups. Okay, I'll just write Z type here instead of write pi bonding or P donating. You've got phenols, okay? So this guy here is going to be strongly electron donating, and it's going to be more reactive than benzene. If we have aniline, there are lone pairs on the nitrogen that cause this aromatic ring to be enriched and activated and more reactive, okay? Now you have molecules that fall in between, and so for example, you know, a phenoxide, for example, would also be activated, all right? You can also have things like various types of ethers. So for example, ethoxybenzene is going to be activated because we have an oxygen atom right adjacent to the aromatic ring with lone pairs. You can also have a variety of esters and things like this. And the thing to focus in on here is that you have a heteroatom, okay, in this case an oxygen with lone pairs right adjacent to the aromatic ring, okay? So don't worry too much about this ketone or this ester group further out. Worry about this part of the aromatic ring that contains a heteroatom right next door with a lone pair of electrons, okay? So any manner of amides, for example, can be electron donating too. Okay, if we've got something like this, well, I'll draw a hydrogen in here, and these lone pairs on the nitrogen are what activate the aromatic ring. Okay, so things like this are going to be strongly electron donating, strongly activators of the aromatic ring. We have the second type, which are sigma donating. Okay, sigma donating electron withdrawal donating groups. Okay, and now it comes back to this idea of carbocation stability. We talked about how things like this generally don't form because they're primary carbocations, and these carbon-hydrogen bonds are very weakly polarized towards carbon, and this methyl group is a very weak electron donating group. It kind of stabilizes the carbocation. Now, if you have 3 methyl groups surrounding a carbocation, that apparently is enough to stabilize it so that it actually does indeed possibly form. So this is a tertiary, it forms. This is a primary, it doesn't. And the whole argument, remember, behind that is that a methyl group is very electron weakly donating just because of all the sigma bonds, okay? It's an inductive effect, basically, where the electrons are flowing in towards the positive charge. So if you have an aromatic ring, for example, like so, and you have an R group, that is a very weak electron donating group, okay? So things like a methyl group or an ethyl group or things like that are going to be very weakly electron donating. The reasoning for that, again, with the carbocations, is that an sp2 hybridized carbon is slightly more electronegative than an sp3 hybridized carbon. So even though we're talking about a carbon-carbon bond, the polarity lies towards the phenyl ring here, just ever so slightly. So definitely, it's a weak effect, all right? So things like ethyl and so on are going to be weak electron donating groups. Okay? So those are the two types of electron donating groups. They activate the aromatic ring and they cause reactivity in the orthopara direction. So I've come up with this phrase, no chops. So nitrogen, oxygen, carbon, and hydrogen, halogens, I'm sorry to say, are orthopara directors, okay? So nitrogen, if it's directly attached to the aromatic ring with lone pairs, okay, with lone pairs on that nitrogen atom, it doesn't matter what those two groups are on nitrogen, that's an orthopara direction. Orthopara director. Oxygen, okay, is also going to be an orthopara director. It doesn't matter what group is off to the right there, okay? Carbon, as I mentioned, is a very weak electron donating group, okay? Very weak electron donating group. So let's just put, like a methyl group here, all right? And halogens. I don't want to talk about halogens right now, but I just want you to remember the phrase, no chops, okay? So this is what I'm calling carbon, okay? Really, it should be R, but it didn't really rhyme well, so no chops is what we have here, okay? So we have nitrogen, oxygen, carbon, and halogens, it turns out, are going to be orthopara directors, okay? So halogens can be chlorine, fluorine, bromine. You're going to see fluorine pop up again in this class. But again, it's just X, okay? So remember, X, don't confuse X with Z. This is chlorine, bromine, could be fluorine, could be iodine, okay? And because of that lone pair, you could think of them as electron donating in and causing those resonance to favor the ortho and para carbon, okay? So remember which groups strongly activate, maybe weakly activate, and remember that these are orthopara directors, okay? We'll talk more about this in the subsequent videos, even though Klein jumps in and kind of presents it at this point. But my emphasis here is that you remember electron donating groups activate the ring, make it more nucleophilic, and therefore more reactive than just standard benzene, okay?